A master boot record is a special type of boot sector at the very beginning of partitioned computer mass storage devices like fixed disks or removable drives intended for use with IBM PC-compatible systems and beyond. The concept of MBRs was publicly introduced in 1983 with PC-DOS 2.0. The MBR holds the information on how the logical partitions, containing file systems, are organized on the medium. Besides that, the MBR also contains executable code to function as a loader for the installed operating system, usually by passing control over to the loader's second stage, or in conjunction with each partition's volume boot record. This MBR code is usually referred to as a bootloader. The organization of the partition table in the MBR limits the maximum addressable storage space of a disk to 2 TB. Therefore, the MBR-based partitioning scheme is in the process of being superseded by the GUID partition table scheme in new computers. A GPT can coexist with an MBR in order to provide some limited form of backward compatibility for older systems. MBRs are not present on non-partitioned media like floppies, superfloppies or other storage devices configured to behave as such. Overview: support for partitioned media, and thereby the master boot record, was introduced with IBM PC-DOS 2.0 in March 1983 in order to support the 10 MB hard disk of the then new IBM Personal Computer XT, still using the FAT12 file system. The original version of the MBR was written by David Litton of IBM in June 1982. The partition table supported up to 4 primary partitions, of which DOS could only use 1. This did not change when FAT16 was introduced as a new file system with DOS 3.0. Support for an extended partition, a special primary partition type used as a container to hold other partitions, was added with DOS 3.2, and nested logical drives inside an extended partition came with DOS 3.30. Since MS-DOS, PC-DOS, OS/2 and Windows were never enabled to boot off them, the MBR format and boot code remained almost unchanged in functionality, except for in some third-party implementations, throughout the eras of DOS and OS/2 up to 1996. In 1996, support for logical block addressing was introduced in Windows 95B and DOS 7.10 in order to support disks larger than 8 GB. Disk timestamps were also introduced, though the description of their actual purpose is not available. This also reflected the idea that the MBR is meant to be operating system and file system independent. However, this design rule was partially compromised in more recent Microsoft implementations of the MBR, which enforce CHS access for FAT16B and FAT32 partition types, whereas LBA is used for the FAT16X and FAT32X partition types. Despite sometimes poor documentation of certain intrinsic details of the MBR format, it was widely adopted as a de facto industry standard, due to the broad popularity of PC-compatible computers and its semi-static nature over decades. This was even to the extent of being supported by computer operating systems for other platforms. Sometimes this was in addition to other pre-existing or cross-platform standards for bootstrapping and partitioning. MBR partition entries in the MBR boot code used in commercial operating systems, however, are limited to 32 bits. Therefore, the maximum disk size supported on disks using 512-byte sectors by the MBR partitioning scheme is limited to 2 TB. Consequently, a different partitioning scheme must be used for larger disks, as they have become widely available since 2010. The MBR partitioning scheme is therefore in the process of being superseded by the GUID partition table. The official approach does little more than ensuring data integrity by employing a protective MBR. Specifically, it does not provide backward compatibility with operating systems that do not support the GPT scheme as well. In the meanwhile, multiple forms of hybrid MBRs have been designed and implemented by third parties in order to maintain partitions located in the first physical 2 TB of a disk in both partitioning schemes in parallel, and or to allow older operating systems to boot off GPT partitions as well. The present, non-standard nature, of these solutions can cause various compatibility problems in certain scenarios though. The MBR consists of 512 or more bytes located in the first sector of the drive. It may contain one or more of a partition table describing the partitions of a storage device. In this context, the boot sector may also be called a partition sector. Bootstrap code, instructions to identify the configured bootable partition, then load and execute its volume boot record as a chain loader. Optional 32-bit disk timestamp. Optional 32-bit disk signature. Disk partitioning. IBM PC-DOS 2.0 introduced the FDISK utility to set up and maintain MBR partitions. When a storage device has been partitioned according to this scheme, its MBR contains a partition table describing the locations, sizes, and other attributes of linear regions referred to as partitions. The partitions themselves may also contain data to describe more complex partitioning schemes, such as extended boot records, BSD disk labels, or logical disk manager metadata partitions. The MBR is not located in a partition. It is located at a first sector of the device, preceding the first partition. In cases where the computer is running a DDO BIOS overlay or boot manager, the partition table may be moved to some other physical location on the device. For example, on-track disk manager often placed a copy of the original MBR contents in the second sector, then hid itself from any subsequently booted OS or application, so the MBR copy was treated as if it were still residing in the first sector. Sector layout. By convention, there are exactly 4 primary partition table entries in the MBR partition table scheme, although some operating systems and system tools extended this to 5 with PTS-DOS 6.60 and Drive-DOS 7.07, 8, or even 16 entries. Partition table entries. An artifact of hard disk technology from the era of the PCXT, the partition table subdivides a storage medium using units of cylinders, heads, and sectors. These values no longer correspond to their namesakes in modern disk drives, as well as being irrelevant in other devices such as solid-state drives which do not physically have cylinders or heads. In the CHS scheme, sector indices have always begun with sector 1 rather than sector 0 by convention, and due to an error in all versions of MS-DOS PC-DOS up to including 7.10, the number of heads is generally limited to 255 instead of 256. When a CHS address is too large to fit into these fields, the tuple is typically used today, although on older systems, and with older disk tools, the cylinder value often wrapped around modulo the CHS barrier near 8 GB, causing ambiguity and risks of data corruption be used. The 10-bit cylinder value is recorded within 2 bytes in order to facilitate making calls to the original legacy INT13 hours BIOS disk access routines, where 16 bits were divided into sector and cylinder parts, and not on byte boundaries. Due to the limits of CHS addressing, a transition was made to using LBA or logical block addressing. Both the partition length and partition start address are sector values stored in the partition table entries as 32-bit quantities. The sector size used to be considered fixed at 512 bytes, and a broad range of important components including chipsets, boot sectors, operating systems, database engines, partitioning tools, backup and file system utilities and other software had this value hard-coded. Since the end of 2009, disk drives using a new technology known as advanced format and employing 4096-byte sectors have been available, although the size of the sector for some of these drives was still reported as 512 bytes to the host system through conversion in the hard drive firmware and referred to as 512 emulation drives. Since block addresses and sizes are stored in the partition table of an MBR using 32 bits, the maximum size as well as the highest start address of a partition using drives that have 512-byte sectors cannot exceed 2T-bar 512-byte sectors are 512 bytes per sector. Alleviating this capacity limitation was one of the prime motivations for the development of the GPT. Since partitioning information is stored in the MBR partition table using a beginning block address and a length, It may in theory be possible to define partitions in such a way that the allocated space for a disk with 512-byte sectors gives a total size approaching 4 terabytes, if all but one partition are located below the 2 TB limit and the last one is assigned as starting at or close to block 232/1 and specify the size as up to 232/1, thereby defining a partition, which requires 33 rather than 32 bits for the sector address to be accessed. However, in practice, only certain LBA48-enabled operating systems, including Linux, FreeBSD and Windows 7 that use 64-bit sector addresses internally actually support this. Due to code space constraints and the nature of the MBR partition table to only support 32 bits, boot sectors, even if enabled to support LBA48 rather than LBA28, often use 32-bit calculations, unless they are specifically designed to support the full address range of LBA48 or are intended to run on 64-bit platforms only. Any boot code or operating system using 32-bit sector addresses internally would cause addresses to wrap around accessing this partition and thereby result in serious data corruption over all partitions. For disks that present a sector size other than 512 bytes, such as USB external drives, there are limitations as well. A sector size of 4096 results in an 8-fold increase in the size of a partition that can be defined using MBR, allowing partitions up to 16 TB in size. Versions of Windows more recent than Windows XP support the larger sector sizes as well as Mac OS X, and the Linux kernel has supported larger sector sizes since 2.6.31 or 2.6.32, but issues with bootloaders, partitioning tools and computer BIOS implementations present certain limitations, since they are often hardwired to reserve only 512 bytes for sector buffers, causing memory to become overwritten for larger sector sizes. This may cause unpredictable behavior as well, and therefore should be avoided when compatibility and standard conformity is an issue. Where a data storage device has been partitioned with the GPT scheme, the master boot record will still contain a partition table, but its only purpose is to indicate the existence of the GPT and to prevent utility programs which understand only the MBR partition table scheme from creating any partitions in what they would otherwise see as free space on the disk, thereby accidentally erasing the GPT. System bootstrapping. On IBM PC-compatible computers, the bootstrapping firmware contained within the RAM BIOS loads and executes the master boot record. The PCXT used an Intel 8088 microprocessor. In order to remain compatible, all x86 architecture systems start with the microprocessor in an operating mode referred to as real mode. The BIOS reads the MBR from the storage device into physical memory, and then it directs the microprocessor to the start of the boot code. Since the BIOS runs in real mode, the processor is in real mode when the MBR program begins to execute, and so the beginning of the MBR is expected to contain real mode machine language instructions. Due to the restricted size of the MBR's code section, it typically contains only a small program that copies additional code from the storage device into memory. Control is then passed to this code, which is responsible for loading the actual operating system. This process is known as chain loading. Popular MBR code programs were created for booting PC-DOS and MS-DOS, and similar boot code remains in wide use. These boot sectors expect the FDISK partition table scheme to be in use, and scans the list of partitions in the MBR's embedded partition table to find the only one that is marked with the active flag. It then loads and runs the volume boot record of the active partition. There are alternative boot code implementations, some of which are installed by boot managers, which operate in a variety of ways. Some MBR code loads additional code for a boot manager from the first track of the disk, which it assumes to be free space that is not allocated to any disk partition, and executes it. A MBR program may interact with the user to determine which partition on which drive should boot, and may transfer control to the MBR of a different drive. Other MBR code contains a list of disk locations of the remainder of the boot manager code to load and to execute. On machines that do not use x86 processors,
or on x86 machines with non-BIOS firmware such as Open Firmware or Extensible Firmware Interface firmware, this design is unsuitable, and the MBR is not used as part of the system bootstrap. EFI firmware is instead capable of directly understanding the GPT partitioning scheme and the FAT file system format, and loads and runs programs held as files in the EFI system partition. The MBR will be involved only insofar as it might contain a partition table for compatibility purposes if the GPT partition table scheme has been used. There is some MBR replacement code that emulates EFI firmware's bootstrap, which makes non-EFI machines capable of booting from disks using the GPT partitioning scheme. It detects a GPT, places the processor in the correct operating mode, and loads the EFI-compatible code from disk to complete this task. Disk identity. In addition to the bootstrap code and a partition table, master boot records may contain a disk signature. This is a 32-bit value that is intended to identify uniquely the disk medium. The disk signature was introduced by Windows NT version 3.5, but it is now used by several operating systems, including the Linux kernel version 2.6 and later. Linux tools can use the NT disk signature to determine which disk the machine booted from. Windows NT uses the disk signature as an index to all the partitions on any disk ever connected to the computer under that OS. These signatures are kept in Windows registry keys, primarily for storing the persistent mappings between disk partitions and drive letters. It may also be used in bootney files, to describe the location of bootable Windows NT partitions. One key where NT disk signatures appear in a Windows 2000/XP registry is key local machine /system /mounted devices /. If a disk signature stored in the MBR was A8HE1HB9HD2H and its first partition corresponded with logical drive C, under Windows, then the reg binary data under the key value /DOS devices /C, would be A8HE1HB9HD2H 0h7A0h0h0h0h0h0h. The first 4 bytes are said disk signature. These are followed by 8 more bytes, forming a 64-bit integer, in Little Endian notation, which are used to locate the byte offset of this partition. In this case, 0h7A corresponds to the hexadecimal value 7E00H. If we assume the drive in question reports a sector size of 512 bytes, then dividing this byte offset by 512 results in 63, which is the physical sector number containing the first sector of the partition. If this disk had another partition with the value 0h F8H93H71H 2 hours following the disk signature, it would begin at byte offset 00027193800H, which is also the first byte of physical sector 20,498,940. Starting with Windows Vista, the disk signature is also stored in the boot configuration data store and the boot process depends on it. If the disk signature changes, cannot be found or has a conflict, Windows is unable to boot. Unless Windows is forced to use the overlapping part of the LBA address of the Advanced Active Partition entry as pseudo-disk signature, Windows usage is conflictive with the Advanced Active Partition feature of PTSD-OS 7 and Drive-DOS 7.07, in particular if their boot code is located outside the first 8 GB of the disk, so that LBA addressing must be used. Programming considerations. The MBR originated in the PCXT IBM PC-compatible computers a Little Endian, which means numeric values spanning 2 or more bytes are stored by the processor in reverse order in memory. The format of the MBR on media reflects this convention. Thus, the MBR signature will appear in a disk editor as the sequence 55H or. The bootstrap sequence in the BIOS will load the first valid MBR that it finds into the computer's physical memory at address 0000H, 7C00H. The last instruction executed in the BIOS code will be a jump to that address, to direct execution to the beginning of the MBR copy. The primary validation for most BIOSes is the signature at offset +1 Fa, although a BIOS implementer may choose to include other checks,
such as verifying that the MBR contains a valid partition table without entries referring to sectors beyond the reported capacity of the disk. While the MBR boot sector code expects to be loaded at physical address 0000H, 7C00H, all the memory from physical address 0000H, 0501H to 0000H, 7FFFH, later relaxed to 0000H, FFFFH the end of the first 640 KI bar is available in real mode. The INT 12 hours BIOS interrupt call may help in determining how much memory can be allocated safely. The last 66 bytes of the 512-byte MBR are reserved for the partition table and other information, so the MBR boot sector program must be small enough to fit within 446 bytes of memory or less. The MBR code may communicate with the user, examine the partition table. Eventually, the MBR will need to perform its main task, and load the program that will perform the next stage of the boot process, usually by making use of INT 13 hours BIOS calls. While it may be convenient to think of the MBR and the program that it loads as separate and discrete, a clear distinction between the MBR and the loaded OS is not technically required. The MBR, or parts of it, could stay resident in RAM and be used as part of the loaded program, after the MBR transfers control to that program. The same is true of a volume boot record, whether that volume is a floppy disk or a fixed disk partition. However, in practice, it is typical for the program loaded by a boot record program to discard and overwrite the RAM image of the latter, so that its only function is as the first link of the bootloader chain. From a technical standpoint, it is important to note that the distinction between an MBR and a volume boot record exists only at the user software level, above the BIOS firmware. To the BIOS, removable and fixed disks are essentially the same. For either, the BIOS reads the first physical sector of the media into RAM at absolute address 7C00H, checks the signature in the last 2 bytes of the loaded sector, and then, if the correct signature is found, transfers control to the first byte of the sector with a jump instruction. The only real distinction that the BIOS makes is that it attempts to boot from the first removable disk before trying to boot from the first fixed disk. From the perspective of the BIOS, the action of the MBR loading a volume boot record into RAM is exactly the same as the action of a floppy disk volume boot record loading the object code of an operating system loader into RAM. In either case, the program that BIOS loaded is going about the work of chain loading an operating system. The distinction between an MBR and a volume boot record is an OS software-level abstraction, designed to help people to understand the operational organization and structure of the system. That distinction doesn't exist for the BIOS. Whatever the BIOS directly loads, be it an MBR or a volume boot record, is given total control of the system, and the BIOS from that point is solely at the service of that program. The loaded program owns the machine. With its total control, this program is not required to ever call the BIOS again and may even shut BIOS down completely, by removing the BIOS ISR vectors from the processor interrupt vector table, and then overwrite the BIOS data area. This is mentioned to emphasize that the boot program that the BIOS loads and runs from the first sector of a disk can truly do anything, so long as the program does not call for BIOS services or allow BIOS ISRs to be invoked after it has disrupted the BIOS state necessary for those services and ISRs to function properly. As stated above, the conventional MBR bootstrap code loads and runs volume boot record code that is located at the beginning of the active partition. A conventional volume boot record will fit within a 512-byte sector, but it is safe for MBR code to load additional sectors to accommodate bootloaders longer than one sector, provided they do not make any assumptions on what the sector size is. In fact, at least 1 KB of RAM is available at address 7C00H in every IBM XT and AT class machine, so a 1 KB sector could be used with no problem. Like the MBR, a volume boot record normally expects to be loaded at address 0000H, 7C00H. This derives from the fact that the volume boot record design originated on unpartitioned media, where a volume boot record would be directly loaded by the BIOS boot procedure. As mentioned above, the BIOS treats MBRs and volume boot records exactly alike. Since this is the same location where the MBR is loaded, one of the first tasks of an MBR is to relocate itself somewhere else in memory. The relocation address is determined by the MBR, but it is most often 0000H, 0600H or 0060H, 0000H. While the MBR code relocates itself, it is still important not to relocate to other addresses in memory because many VBRs will assume a certain standard memory layout when loading their boot file. The status field in a partition table record is used to indicate an active partition. Standard conformant MBRs will allow only one partition marked active and use this as part of a sanity check to determine the existence of a valid partition table. They will display an error message if more than one partition has been marked active. Some non-standard MBRs will not treat this as an error condition and just use the first marked partition in the row. Traditionally, values other than 0-hour and 80H were invalid and the Bootstrap program would display an error message upon encountering them. However, the plug-and-play BIOS specification and BIOS boot specification allowed other devices to become bootable as well since 1994. Consequently, with the introduction of MS-DOS 7.10 and higher, the MBR started to treat a set bit 7 as active flag and showed an error message for values 1-hour 7FH only. It continued to treat the entry as physical drive unit to be used when loading the corresponding partitions VBR later on, thereby now also accepting other boot drives than 80H as valid. However, MS-DOS did not make use of this extension by itself. Storing the actual physical drive number in the partition table does not normally cause backward compatibility problems, since the value will differ from 80H only on drives other than the first one. However, even with systems enabled to boot off other drives, the extension may still not work universally. For example, after the BIOS assignment of physical drives has changed, for example when drives are removed, added or swapped. Therefore, per the BIOS boot specification, it is best practice for a modern MBR accepting bit 7 as active flag to pass on the DL value originally provided by the BIOS instead of using the entry in the partition table. BIOS to MBR interface. The MBR is loaded at memory location 0000H, 7C00H and with the following CPU registers set up when the prior Bootstrap loader passes execution to it by jumping to 0000H, 7C00H in the CPU's real mode. CS, IP equals 0000H, 7C00H. Some compact BIOSes erroneously use 07C00H, 0000H instead. While this resolves to the same location in real mode memory, it is non-standard and should be avoided, since MBR code assuming certain register values or not written to be relocatable may not work otherwise. DL equals boot drive unit. DL is supported by IBM BIOSes as well as most other BIOSes. The Toshiba T1000 BIOS is known to not support this properly, and some old YS-286 BIOS use DL values greater or equal to 2 for fixed disks. USB sticks configured as removable drives typically get an assignment of DL equals 80H, 81H, etc. However, some rare BIOSes erroneously presented them under DL equals 1 hour, just as if they were configured as superfloppies. A standard conformant BIOS assigns numbers greater or equal to 80H exclusively to fixed disk/removable drives, and traditionally only values 80H and 0-hour were passed on as physical drive units during boot. By convention, only fixed disk/removable drives are partitioned, therefore, the only DL value a MBR could see traditionally was 80H. Many MBRs were coded to ignore the DL value and work with a hardwired value, anyway. The plug-and-play BIOS specification and BIOS boot specification allow other devices to become bootable as well since 1994. The latter recommends that MBR and VBR code should use DL rather than internally hardwired defaults. This will also ensure compatibility with various non-standard assignments, as far as the MBR code is concerned. Bootable CD-ROMs following the El Torito specification may contain disk images mounted by the BIOS to occur as floppy or superfloppies on this interface. DL values of 0 hour and 1 hour may also be used by protected area runtime interface extension services and trusted computing group BIOS extensions in trusted mode to access otherwise invisible parties partitions, disk image files located via the boot engineering extension record in the last physical sector of a hard disk's host protected area. While designed to emulate floppies or superfloppies, MBR code accepting these non-standard DL values allows to use images of partitioned media at least in the boot stage of operating systems. DH bit 5 equals 0, device supported through INT 13 hours. Else, don't care. DH is supported by some IBM BIOSes. Some of the other registers may typically also hold certain register values with original IBM RAM BIOSes, but this is nothing to rely on, as other BIOS may use other values. For this reason, MBR code by IBM, Microsoft, Digital Research, etc. never did take any advantage of it. Relying on these register values in boot sectors may also cause problems in chain boot scenarios. Systems with plug-and-play BIOS or BBS support will provide a pointer to PNP data in addition to DL. DL equals boot drive unit, ES. DI equals points to $PNP installation check structure. This information allows the bootloader in the MBR to actively interact with the BIOS or a resident PNP/BBS BIOS overlay in memory in order to configure the boot order, etc. However, this information is ignored by most standard MBRs and VBRs. Ideally, ES, DI is passed on to the VBR for later use by the loaded operating system, but PNP-enabled operating systems typically also have fallback methods to retrieve the PNP BIOS entry point later on so that most operating systems do not rely on this. MBR to VBR interface. By convention, a standard conformant MBR passes execution to a successfully loaded VBR, loaded at memory location 0000H, 7C00H, by jumping to 0000H, 7C00H in the CPU's real mode with the following registers maintained or specifically set up: CSIP equals 0000H, 7C00H, DL equals boot drive unit, MS-DOS 2.0-7.0/PC DOS 2.0-6.3. MBRs do not pass on the DL value received on entry, but they rather use the boot status entry in the partition table entry of the selected primary partition as physical boot drive unit. Since this is, by convention, ATH in most MBR partition tables, it won't change things unless the BIOS attempted to boot off a physical device other than the first fixed disk/removable drive in the row. This is also the reason why these operating systems cannot boot off a second hard disk, etc. Some FDISK tools allow to mark partitions on secondary disks as active as well. In this situation, knowing that these operating systems cannot boot off other drives anyway, some of them continue to use the traditionally fixed value of ATH as active marker, whereas others use values corresponding with the currently assigned physical drive unit, thereby allowing to boot off other drives at least in theory. In fact, this will work with many MBR codes, which take a set bit 7 of the boot status entry as active flag rather than insisting on ATH. However, MS-DOS PC-DOS MBRs are hardwired to accept the fixed value of ATH only. Storing the actual physical drive number in the partition table will also cause problems when the BIOS assignment of physical drives changes, for example when drives are removed, added or swapped. Therefore, for a normal MBR accepting bit 7 as active flag and otherwise just using and passing on to the VBR the DL value originally provided by the BIOS allows for maximum flexibility. MS-DOS 7.1-8.0 MBRs have changed to treat bit 7 as active flag and any values 1 hour 7 FH as invalid, but they still take the physical drive unit from the partition table rather than using the DL value provided by the BIOS. Dr. DOS 7.07 extended MBRs treat bit 7 as active flag and use and pass on the BIOS DL value by default, but they also provide a special NEWLDR configuration block in order to support alternative boot methods in conjunction with loader and real/32 as well as to change the detail behavior of the MBR, so that it can also work with drive values retrieved from the partition table. translate-wise non-standard drive units 2 hours 7FH to 80H FDH, and optionally fix up the drive value or at sector offset +1 FDH, in loaded VBRs before passing execution to theme Euro. This also allows other bootloaders to use NEWLD as a chain loader, configure its in-memory image on the fly and tunnel the loading of VBRs, EBRs, or AAPs through NEWLDR. The contents of DH and ES, DI should be preserved by the MBR for full plug-and-play support. However, many MBRs, including those of MS-DOS 2.0-8.0/PC-DOS 2.0-6.3 and Windows NT XP, do not. Some MBRs set DH to 0. The MBR code passes additional information to the VBR in many implementations. DSSI equals points to the 16-byte MBR partition table entry corresponding with the activated VBR. PCMOS 5.1 depends on this to boot if no partition in the partition table is flagged as bootable. In conjunction with loader, multi-user DOS and real/32 boot sectors use this to locate the boot sector of the active partition if the boot file could not be found. PTSDOS 6.6 and SDOS 1.0 use this in conjunction with their advanced active partition feature. In addition to support for loader and AAPs, Dr. DOS 7.07 can use this to determine the necessary INT 13 hours access method when using its dual CHS LBA VBR code, and it will update the boot drive/status flag field in the partition entry according to the effectively used DL value. Darwin bootloaders depend on this pointer as well, but additionally they don't use DS, but assume it to be set to 0000H instead. This will cause problems if this assumption is incorrect. The MBR code of OS/2, MS-DOS 2.0 to 8.0, PC-DOS 2.0 to 7.10 and Windows NT XP provides this same interface as well, although these systems do not use it. The Windows Vista/7 MBRs no longer provide this DS/SI pointer. While some extensions only depend on the 16-byte partition table entry itself, other extensions may require the whole 4-partition table to be present as well. DS/BP equals optionally points to the 16-byte MBR partition table entry corresponding with the activated VBR. This is identical to the pointer provided by DS/SI and is provided by MS-DOS 2.0-8.0, PC-DOS 2.0-7.10, Windows NT XP 7 MBRs. It is, however, not supported by most third-party MBRs. Under Drive DOS 7.07 an extended interface may be optionally provided by the extended MBR, and in conjunction with loader, AX equals magic signature indicating the presence of this NEWLDR extension. DEL equals boot drive unit, DS/SI equals points to the 16-byte MBR partition table entry used, ES. BX equals start of boot sector or NEWLDR sector image, CX equals reserved, in conjunction with GPT. An enhanced disk drive specification for hybrid MBR proposal recommends another extension to the interface, EAX equals 54,504,721H, DL. Equals boot drive unit, DS/SI equals points to a hybrid MBR handover structure, consisting of a 16-byte dummy MBR partition table entry followed by additional data. This is partially compatible with the older DS/SI extension discussed above, if only the 16-byte partition entry, not the whole partition table, is required by these older extensions. Since older operating systems do not support this extension nor are they able to address sectors beyond the 2 TB barrier, a GPT-enabled hybrid bootloader should still emulate the 16-byte dummy MBR partition table entry if the boot partition is located within the first 2 TB. ES/DI equals points to $PNP installation check structure, editing replacing MBR contents, though it is possible to manipulate the bytes in the MBR sector directly using various disk editors. There are tools to write fixed sets of functioning code to the MBR. Since MS-DOS 5.0, the program FDISK has included the switch/MBR, which will rewrite the MBR code. Under Windows 2000 and Windows XP, the recovery console can be used to write new MBR code to a storage device using its FIX MBR command. Under Windows Vista and Windows 7, the recovery environment can be used to write new MBR code using the bootrex/FIX MBR command. Some third-party utilities may also be used for directly editing the contents of partition tables, such as MBRwizard. DD is also a commonly used POSIX command to read or write to any location on a storage device, MBR included. In Linux, MISs may be used to install a Windows MBR. The Grub and Lilo projects have tools for writing code to the MBR sector, namely Grub Install and Lilo MBR. The Grub Legacy Interactive Console can write to the MBR, using the setup and embed commands, but GRUB2 currently requires Grub Install to be run from within an operating system. Various programs are able to create a backup of both the primary partition table and the logical partitions in the extended partition. Linux SFDISK is able to save a backup of the primary and extended partition table. It creates a file that can be read in a text editor, or this file can be used by SFDISK to restore the primary extended partition table. An example command to back up the partition table is sfdisk-dhda-hda-out and to restore is sfdisk-hda-hda-out. It is possible to copy the partition table from one disk to another this way, useful for setting up mirroring, but it should be noted that sfdisk executes the command without prompting warnings using sfdisk-dsda-sfdisk-sdb. See also. Notes. References. Further reading, H. Gilbert. Partitions and Volumes. PC Lube and Tuner, Ray Knights. Ray's Place. MBR and Windows Boot Sectors A, Hale Landis. Master Boot Record. How It Works A, Daniel B. Sidori. MBRs. Boot Records Revealed. A, External Links, article on Master Boot Record.